Hi, I'm going to work through the answers to the fourth homework, and the first problem was number 8 on page 442. It reads this way: suppose you made a scatter plot for the rates of illiteracy within city blocks and the rates of drug-related crime. How would you expect the scatter plot to look? Okay, so rates of illiteracy within city blocks and the rates of drug-related crime. Well, I would probably put the illiteracy rates on the independent axis. So let's put illiteracy rates. And drug-related crime goes up here on the dependent axis. Drug-related crime. Does that make sense? I mean, would it be okay to switch those axes? Of course it could. But probably if you were interested in studying something like this, you would want to look at illiteracy rates, and then based on that illiteracy rate, you probably want to see, well, how does that correspond to the drug-related crime rate? So to me, it would seem more natural to make the crime rate dependent upon illiteracy rates. But it would not be wrong to get those reversed. I just think it would be more natural to do it this way. And by the way, the unit is by city block. So, alright, so what would a scatter plot tend to look like? Well, let's see. As the illiteracy rates climb, would you expect there to be more drug-related crime? You know, fewer people can read means, you know, those are people who have a harder time getting a job, a steady job, and keeping it, and a nice, decent job. So I would expect that as the illiteracy rates climb, then there's probably going to be an upward trend in drug-related crime. So the regression line would probably have a positive slope. There would be a positive correlation here. And so let's see. In which direction would the point seem to scatter upward or downward from the x-axis? Upward or downward from the x-axis? Well, I assume they meant as you go to the right, it would go upward. Positive correlation. So that's what I would expect. And what would this directional flow at data points mean to the statistically acute observer? Well, you probably look at that and probably verify the almost obvious that when there's increased illiteracy rates, you expect drug-related crime to rise. So anyway, now that may be a bias on my part and perhaps your part, that that's what's going to happen. We just expect that to happen. Is it really true? I don't know. But you know, this is what I expect to happen, and maybe this is a bias on my part, thinking that the more educated you are, the less likely you are to, you know, participate in this kind of activity. So anyway, that would be my expectation. Now, what if you had these reversed, just for sake of argument? Would we have the same type of thing happen? So if I had crime down here and illiteracy up here, would we still expect a positive correlation? Well, as drug-related crime increases, I would expect there to be greater illiteracy. So I would think it would seem to be that it doesn't matter if you have those reversed on the axes, you're still going to probably expect a positive correlation there, positive slope. So anyway, that's problem number 8. Problem number 32 is another, on page 445, number 32, another one related to crime. I guess the authors are kind of fixated on that. So let's read the problem here. You have data on crime rates for each of the 48 contiguous states, and you would like to know whether different types of crimes are related. When you do a regression analysis of larceny rates as dependent variable on robbery rates, as dependent variable on the robbery rates as the independent variable, you find, and they have this regression equation. So they've got it larceny is equal to 2,682 plus 1.49 times the robbery rate. All right, so as far as a graph, then we would put larceny on the y-axis. It's the dependent variable, and we have robbery down here on the independent variable axis. And let me see, the regression line goes something like this. All right, so in other words, that the y-intercept is 2,682, and the slope is 1.49 times robbery. So first of all, what's the difference between robbery and larceny? I believe that larceny is stealing without force, in other words, by stealth. And so if someone broke into your house when you weren't there, that would be larceny. However, if you got held up by someone or mugged, that would be robbery. Okay, so when a guy walks into a gas station with a gun and demands money, that's robbery. It's stealing by force. Shoplifting, is that larceny? I think that probably is larceny, because you don't shoplift by force, you just steal by being sneaky. So anyway, I think that's the more or less the definitions there on that. And should they be related? You know, do the same people do the same type of crimes? There are probably a lot of people who are larcens who would never even think about trying to steal by force. You know, that would never think about you know, forced robbery. And there might be a few guys who only steal by force because they're just thugs. I don't know. That's just a speculation. But anyway, there's the regression line, and they have some other information here. They gave us the t-score. The calculated t-score was 2.05, and there are 46 degrees of freedom, and the p-value is 0.023. All right, so what does all that mean? Well, N was 48, and they told us that because this was based on the 48 contiguous states, so the sample size was 48. In a regression analysis with two variables, degrees of freedom will be N minus 2. The t-score, you know, this stuff really doesn't do anything for us except it gets us to the p-value. And the p-value tells us that there really is a positive correlation here. We know it's positive because the coefficient here of robbery, the slope is positive, 1.49. That means that for every robbery, there are 1.49 larcenies. I'm sorry, for every increase in the robbery rate, the larceny rate goes up by about 1.49. So, but this tells us that because the p-value is less than 0.05, that there is a significant positive correlation. And we can conclude that with 97.7% confidence. Okay. So let's answer the book questions in Part A. What conclusion can you draw about the relationship between larceny and robbery from this analysis? I conclude that larceny is related to robbery. There is a correlation, positive correlation between robbery and larceny. As robbery increases by state, larceny goes up by about 1.5 times, about 50%. So anyway, that would be my conclusion, positive correlation. And let's see. Now they don't tell us what the correlation coefficient is. I'll show you how to calculate that here in a minute. The Part B, what are some of the conclusions you cannot draw about the relationship from this analysis? Well, you cannot conclude that there is a cause and effect relationship. In other words, if you manage to decrease the robbery rate, would it also decrease the larceny rate? I don't know. Because, like I said, it could be different types of people doing each type of crime. And so there may not be a strong cause and effect relationship. Now, if everyone who stole was willing to do it by force or by stealth, then In other words, if you're equal opportunity thief, you didn't care if you stole by force or by being sneaky, then perhaps there is a cause and effect relationship. Don't know, but we don't have enough information to answer that. So, okay, now I expect probably a lot of people would say, well, we don't know what the correlation coefficient is. Well, we can calculate it, and so let me show you that. And if you look on the bottom of page 441, it gives the t-score. T is equal to r over the square root of 1 minus r squared over n minus 2. Now, we can solve for r, and I've solved it. I haven't written in my book, so I'll spare you all the algebra, but if you solve for r happens to be equal to t divided by the square root of n minus 2 plus t squared. So here's a formula not in your book, but if you solve for r, you'll get r equals t divided by square root n minus 2 plus t squared. So with that, we can actually calculate the r. And so if I plug in my numbers, 2.05 for t divided by n minus 2, that's basically the degrees of freedom here. Degrees of freedom, which was 46 in this case, plus t squared, 2.05 squared. Well, let's see what we get here. So 46 plus 2.05 squared. And now I'm going to square that. Oops, take the square root. Yeah, I screwed up. Let me try that. 46 plus 2.05 squared, hit equal. I'll take the square root, and I'll take 2.05 and divide it by that answer. And I get r equals to 0.29. So there's a weak correlation because the correlation coefficient was in the weak category, weak positive correlation. So weak positive correlation with r equals 0.29. And if we square that number, 0.29 squared is 0.0841. So in other words, about 8% of this data is explained by a relationship between robbery and larceny, and the other 92% is explained by residual factors. So the odds that there's a cause and effect relationship seem to be pretty remote here. But in any event, we know that only 8% of this is explained by this relationship between robbery and larceny, and the other 92% is due to residual factors. So in other words, the scatter plot is probably pretty scattered. You know, there's an upward trend, but it's probably all over the place. So anyway, that's my interpretation of this. Problem 36 starts on the bottom of page 447. And so let's talk through it. Many factors affect poverty, and education may be one of them. One way to study the relationship between these two variables would be to collect data from individuals on the amount of education they have and the size of their income. In this exercise, the data are not on individuals, but on states. From the Census Bureau, we find that the percentage of the adult population in each state that has a 9th grade education or less, and the percentage of the population with income below the official poverty level. So regressing the percentage below the poverty line on the percentage with 9th grade education or less for the 50 states and the District of Columbia gives, all right, so I'm going to write out this line here. Percent poor is equal to 4.6 plus 0.8 times the percent with a low education. And our other data here is that R is 0.70. That would be a moderate correlation, but it is on the high side. So it's close to a strong correlation, but still considered moderate. The t-score they found was 6.72, 49 degrees of freedom, which meant that the sample size was 51, 50 states plus District of Columbia, and then p is less than 0.0001. All right, 3 zeros and a 1. So what does part A? What does the value of 0.8 of the regression coefficient tell us? 0.8 is the slope. And it says that for every percent increase in low education, there's a 0.8% increase in the percent of poor. So why don't we skip down to the regression line, which is closer to the bottom of the page. The regression line goes off like this, and there's a lot of dots all over the board, all over the page. And down below we have percent with 9th grade educational left. So percent with, I'll call it low education. And here's percent that are considered below the poverty level. So each point represents a state. One of the 51 states are District of Columbia. And it's rising. There's a positive correlation. So what does the slope tell us? For every 0.8% increase in low education, I'm sorry, let me try that again. For every 1% increase in low education, there's a 0.8% increase in the poverty level. So if you increase by 1% this way, you go up by 0.8% that way in the poor. So anyway, that's what that tells us, the slope. It's a rate of increase. What is the probability of a correlation coefficient of 0.70 or more by chance alone in a sample of 51 observations from a population with a correlation coefficient equals to 0? Okay, so they just described the hypothesis test to see is there what are the odds? So the hypothesis test, the null hypothesis, is that the population correlation coefficient, Greek letter rho, is equal to 0. The alternative in this case would be that it's greater than 0, because that's what we observed. We observed a sample correlation greater than 0. So that would be our alternative. So when they're asking what are the odds of this population having no correlation if we get a sample with 0.70, and the probability would be the p-value, less than 1 in 10,000, less than 0.0001. So that would be the probability. The probability literally is the p-value of this scenario happening. So, okay, part C. The scatter plot of these data is shown in the figure. Why are some of the points above the regression line and why are some below the regression line? Well, that's due to residual factors, isn't it? And so the poverty rate is not strictly tied to the educational rate. Whoops, telephone, be right back. I'm back. Where was I? Part C. The scatter plot is shown in the figure. Why are some of the points above the regression line and some below the line? Well, again, that was the due to residual factors. So there's some randomness involved here, and not everything is strictly tied. If you had a perfect correlation, then all these points would be on the line. If the poverty rate was strictly tied to the education rate, then everything would be on the line. R would be 1 and be a perfect correlation. Because it's not, there are residual factors affecting the poverty rate. What might they be? Residual factors. It could be the economy in each state, how each state's run. Some states have such high taxes, they're basically scaring businesses off. Some states have very good employment opportunities, lots of jobs available, and business-friendly atmosphere. So there are a lot of things here. Cost of living is probably higher in the north than it is in the south due to various factors like heating your home in the winter. And so there's all kinds of other factors thrown in there. So residual factors explains part C. Now here we go. This, I think, part D and E are very interesting questions. Part D, the states with the largest negative residuals are New Jersey, Connecticut, Hawaii, Rhode Island, and Virginia. What might be some of the reasons that these states lie below the regression line? All right, when it's talking about negative residuals, that means that the reason a state goes below the line is because it has a negative residual. And so those 5 states, I think it was 5 states, all lie below the line. Now what might be some of the reasons these states lie below the line? Well, let's compare 2 things here. Suppose I'm going to take this state and compare it with that state, with the regression line. So this is the average. And for this amount of education, then those states, those 5 states, including Hawaii, have fewer people in the poverty level. So the negative residuals here is good. And so even though they, for this amount of education, they have fewer people below the poverty rate. That's a good thing. And so you can only, that type of question, you only can compare it to other things at that same independent variable, that same x value. And part E goes the other way. It says the states with the largest positive residuals are Mississippi, Louisiana, New Mexico, Montana, and Utah. What might be some of the reasons that these states lie above the regression line? All right, so if they're above the regression line, here for example, then they have a higher poverty rate on average compared to the same amount of education. So it really, questions D and E do not really refer to comparing different educational levels. It refers to take the same educational level, compare it to something else. Because some states are below the line, they have a lower poverty rate. Okay, why do they have a lower poverty rate? Well, maybe the wages are better in those states. Maybe it pays better. What about the states with the positive residuals that are above the line, like Mississippi? Well, maybe pay is really low in Mississippi, and so that kicks up the poverty rate. And so, anyway, I'm really interested in you knowing the difference here. Why is something, or what does it say when something is below the regression line as compared to something above the regression line? In this case, it would be better to be below the regression line in this problem, wouldn't it? Because it means that even though for this amount of education, their poverty rate's lower, that means opportunities for pay are better in that state. So, anyway, that's, are there other reasons? Oh, we could probably cook up other reasons. I'm mostly interested in you seeing why something is off the regression line. How does it compare? So, anyway, that's problem number 36. Problem 40, page 450. This one's always amused me. A well-known statistician collected and analyzed data on the height in inches of fathers and their children. She found the following results. So she has the offspring height equals to 1.52. So offspring height is equal to 1.52 plus 0.75 times the father's height. There we go. And then they have all this other stuff there. R equals to 0.59. R squared is 0.34. And then T is 2.90. P is 0.0051. And N was 18. Alright, so collected and analyzed data on height in inches of fathers and their children. Now what amuses me about this problem, it says it looks like these kids are only 3/4 the size of their father's height. Because that's the slope, right? So if the father is 6 foot tall, 3/4 of 6 feet is 4.5 feet, 4 foot 6 inches. So it means the offspring will be 4 foot 7.5 inches tall. Boy, that's pretty short. So a 6'5" father produces a 4 foot 7.5 inch tall kid. That's why it amuses me, and I think what they're leaving out is what ages were these children at the time of this measurement, where they probably were all the same age. Okay, or perhaps this was actually inches over a certain amount. Maybe it's inches over 5 feet. So if it was inches over 5 feet, then a 6 foot tall father is 12 inches taller than 5 feet. 3/4 of that is 9 inches. Add 1.5, that's 10.5 inches. So the offspring on average would be 5 foot 10.5. That seems to be closer to some kind of reality there, because some kids will be shorter than the fathers. Some of the daughters most likely are likely to be shorter than fathers in most cases, I would expect. And so I don't know. Anyway, that's just speculation. They don't tell us all that information here, but I was looking at this. Seems kind of strange. Why don't they give us the full story here? So anyway, what do the Part A. What do the results of the statistical analysis tell you about the relationship between the two variables? Well, that relationship is a positive correlation because of the positive slope, or you could say the positive correlation coefficient. So in other words, the taller fathers produce taller offspring, just like you would expect. What else does it tell us? It tells us that the relationship is moderate because the correlation coefficient was 0.59, moderate. 34%, R squared, 34% of this relationship is, 34% of the data is explained by the relationship between the father and the offspring. 66% would be due to residual factors like the mother and other things like health and diet and that sort of stuff. So 34% is explained by this relationship. And they did a hypothesis test, which the only hypothesis test we have here is this correlation significant? Yes, it is, because the p-value is very, very small, less than 0.00. It's 0.0051, far less than 5%. So we would say yes, this is a significant positive correlation. Do the hypothesis test. And what's the sample size? Well, it's 18. Okay, so there you go. Part B, the 95% confidence interval for the population regression coefficient is 0.20 to 1.30. What is the interpretation of this interval? Now, I don't think that's very obvious what in the world they're talking about there. You can't have... they're not talking about the correlation coefficient, because the correlation coefficient can only go up to 1. And so when I finally figured this out, I took the average of 0.20 and 1.30. So if you add 0.2 and 1.3 together, you get 1.5 divided by 2, you get 0.75. They're talking about the slope. So I think it would have been a lot clearer if the authors had said, referred to it as slope rather than the population regression coefficient. And so and do they even have a calculation for that? Well, yes, they do. Actually, page 441, they do have a confidence interval, middle of the page, confidence interval for the population regression coefficient beta. All right, now, what's the interpretation of this interval? That means there's a 95% chance that the population slope falls between 0.2 and 1.30. 95% probability that happens. So now that hypothesis test on whether the slope is positive or whether the correlation coefficient is positive is the exact same test, and it's because the only way a slope can be 0 is if the correlation coefficient is 0. It's the same hypothesis test, but they're referring to a confidence interval based on the slope. So, which I'm not going to ask you to calculate those, but it's in the book, and that's what they're talking about. There's a 95% probability, at least, that that the slope falls between 0.2 and 1.30. So anyway, that's problem number 40. Problem 44 on page 453. The annual college guide from U.S. News and World Report has a wealth of data on a large number of colleges and universities. The meaning of the rankings is debatable, but college schools do like to be ranked high. I went to University of Southern California and they claim to be in the top 25 in everything, which I thought was kind of amazing. Oh well. So look at the dozen top ranked national universities, excluding California Institute of Technology, and how much they spend on each student in a year in the table on page 454. The spending figure comes from dividing the annual budget by the number of students and is higher than the tuition and fees because the schools subsidize students from other incomes. Indeed they do. So here we go. The table's on top of page 454, and you have Harvard ranked number 1, and they spend $36,000 per year on students. Okay, and then Northwestern is at the bottom there at 12, and they spend $25,000 a year. So in a scatter plot of these data, some schools lie above the regression line and some lie below it. A regression analysis of rank on spending gives a line with this equation. So the rank equals to 17 minus 0.34 times the spending. 34 times the amount spent, and I think that's in thousands of dollars. What do they call it? Spending. And R was equal to minus 0.60. So if that is a significant correlation, then the correlation would be a moderate negative correlation. And it's negative because the slope is negative. So now the book says the relationship is negative because highest ranked Harvard has the lowest numerical rank and is therefore located at the bottom of the scatter plot. The Northwestern with rank 12 is located at the top of the scatter plot. So if we did a scatter plot on this, the rank is the dependent variable. Here's 17, and here's spending. So the regression line goes like this, and so in other words, we expect that schools that spend more on their students tend to have a lower rank number. Now, a lower rank number is good. If you're ranked number 1, you're number 1, and so actually this makes sense. If they spend more, you expect to have a higher ranked college would mean a lower ranking number. All right, so what is the implication for a school if its data point is located below the regression line? All right, so if you're below the regression line, that means for that amount of spending, you have a better ranking, a lower ranking number. So your ranking is better. That would be good, wouldn't it? And so a good thing that if you spend this amount, that you get a better ranking on average than other schools. So that's part A. And part B, do schools located below the regression line have anything in common? Yeah, I would say you get a better bang for your buck. So if you're below the regression line, yeah, what they have in common is that they tend to have a better ranking based upon the amount spent on students. So I don't know if anything else they have in common, but that would be, I think, pretty clear there. Part C, what is the average difference in rank between schools that differ by $3,000 in spending per student per year? All right, so remember, this is in thousands of dollars. So if I take my slope and multiply it by, was it $3,000? Which I'll write as, it looks like $3, but it's really meant to be in thousands of dollars, so that's times $3,000. This would be about, what, 1.02 would be the rank. And so if a school spends an extra $3,000 on students, they expect to come up in the rankings by about one rank number. So in other words, if you're ranked number 9 on the list, and you decide this year you're going to be able to spend another $3,000 on students, your ranking you expect would probably jump to 8, from 9 to 8, based upon this analysis. Now, is there a cause and effect relationship there? We can't say. We can't say that that would force you to get a better ranking, but it could, according to this analysis. But that would be the average difference in rank. So if you increase spending by 3,000 increase, then the rank drops by about one point. So problem 46 on page 455. The New York Times once commissioned a laboratory to analyze a dozen slices of pizza from different stores in New York City for calories and fat content. The slices ranged in weight from 5.25 to 10.5 ounces, and calories from 366 to 613, and in fat from 11 to 25 grams. So a regression analysis of calories on grams of fat yields the following results. I wrote everything up here, and here's a regression line where calories is the dependent variable and grams of fat is independent. And here's all this information given in the book. But I also squared R and got R squared because that's important. Okay, I really expect you to think about R squared. So whenever you can, square R. Tell me what R squared means. And otherwise, I'm going to dock you for not giving me enough information. So part A. What do these numbers tell you about the relationship between the two variables? Well, it's the p-value tells us that there's a significant positive correlation. Well, okay, the slope is positive, or you can say the correlation coefficient is positive, but the p-value tells you that that's statistically significant. So with better than 99% confidence, we can conclude that there really is a correlation between grams of fat and calories. It's not strictly random. So there is a relationship, a correlation. The correlation is strong positive. It's in the 0.78 range, makes it the strong positive correlation range. The R squared tells you that 61% of these results are explained by the relationship between grams of fat and calories. 61%, 39% is due to residual factors. So, what else can we conclude here? They analyzed 12 slices of pizza because the degrees of freedom were 10. So they took pizza from probably 12 different pizza joints in New York City and did all this analysis. So that's, I think, what we can conclude in part A. Now part B is where it gets interesting. And I've decided not to grade part B. I'll just, provided you wrote something that made some sense. And so I'll expect you to answer something here. But I have a confession to make. I've been going over this problem for years, and I just now took my own data. I made up my own data, and I may email this to you if you're my student. I just made up my own data and created a regression line for pizza. I made up grams of fat and calories, and I made up the weights of pizzas. So anyway, let's read the question. Suppose you had divided the calories and fat for each slice by the weight of the slice. How do you think that would affect the analysis? That should be affect, not effect. I think that would be the correct word. All right, possibly effect works there as a verb. It's rare to use effect as a verb. But anyway, how would that affect the analysis? I used to think it wouldn't change it, but it does. The weight of the slice of pizza is really weighting these numbers, isn't it? You know, a larger pizza contains more grams of fat, contains more calories, and it does change the data. And so when I just made up my own data and then divided by the slices, the weight of the slices of my hypothetical pizzas, everything changed. The intercept changed, which did surprise me. The slope changed, which sort of surprised me. And the correlation coefficient changed, which really surprised me. So it does matter. The size of the slice of pizza, as it turns out, does matter. in this problem. And I wouldn't expect you to really know that definitively unless you did something like I did, made up your own data. So I got surprised on this one. And but it really does depend upon slice of pizza, the size, or weight rather, the weight of the sliced pizza. Now, if you're not concerned about how much a pizza slice weighs, if you think, well, people just eat one slice at a time, or they eat 2 slices or 3 slices at a meal, then perhaps this analysis is great. But if you're talking about fat content versus calories in pizzas, then I think you would need to do that dividing out. In other words, you want to compare per ounce. And so if you divided a pizza by its weight, then you're getting how many fat per ounces and how many calories per ounce. Fat per ounce and calories per ounce. And if you're making your analysis on that basis, on the weight of pizza, then you want to divide the weight of pizza out so that that's gone. And that's going to change the analysis, as it turns out. So that was a bit of a surprise to me. Like I said, I've talked to this problem for years and never really did my homework on it, but now I did. And actually, the answer to part B is you can't predict it. Okay, it's going to change all the numbers, and as I found out for myself. So anyway, that's problem number 46. This is problem 1050, or number 50, on page 457. The road distance from one city to another is usually longer than the direct distance. In a sample of English cities, the regression equation for these distances was road distance equals to 7 plus 1.17 times the direct distance. And they don't tell us if this was miles or kilometers. Well, in any event, what does this equation tell you about the direct distance versus the road distance in England? Well, it's road distance is approximately 17% longer than direct distance. Now you also have this intercept number. So, for example, if here are 2 cities in England, London, and I don't know what's another England city. Ipswich, I don't know. They have neat names over there. Ipswich, I think that's a city over there. I don't know where it is. But anyway, and I have of course I have no idea how far apart they are. But suppose that the direct distance was 100 miles. Then the road distance would be 1.17 times 100, so it would be 117 plus 7, 124 miles. All right, so there's the average road distance. So it's about 17% more, but actually a little bit more because of the slope number. So it's stating the obvious that the road distance is longer than direct distance. And now it doesn't tell us the correlation, doesn't give us a p-value, any of that stuff. So we don't know if this correlation is significant, if it's strong, if it's weak. We don't know. I suspect it's a fairly strong correlation, but that's just a guess. It really depends upon how windy the roads are in England. Okay, and this looks pretty good to me. It says that, okay, well, they don't build roads normally in a straight line from one city to another. You have to go around the countryside and take some corners and curves. And so it's saying that basically it's about 17% more plus a few extra miles. So I'm not sure what else we could say about this, but I thought it was an interesting analysis.